Welcome to MOOC course on Introduction to Proteogenomics. Interpretation of mass spectrometry data is very challenging. There are many softwares which are commercially available or open source softwares which make our job relatively very easy. However, the basic knowledge of mass spectrometry data and its interpretation becomes very crucial. In the last lecture, you were introduced to the basic concepts of mass spectrometry and sample preparation. Today we have a hands-on session which aims to provide some basic knowledge required for the manual interpretation of mass spectrometry data. Let us welcome Dr. Karl Klauser for today's hands-on session.
Now, other than to say that we're going to try to assign fragment ion types, and these are the things you should keep in mind for the various fragment ion types. One of the things I didn't mention so far is that there are ammonium ions which give you composition information, but they don't give you stoichiometry. Okay? So if you see a 120 ion in your spectrum, that's a good indication that you have phenylalanine. But if you have a really tall 120, it doesn't mean you have 2 or 3 of them. Okay, so you don't have the stoichiometry information. In order to form an ammonium ion, the fragmentation has to occur in 2 places along the peptide backbone, and it includes the side chain that is unique to the amino acid. Okay, all right. By the techniques that we're going to be using in the spectra that are being shown, the ammonium ions that are likely to be present are shown in green. Okay? The ones that are shown in black are essentially not, you can only form those if you have a high energy collision type of instrument, which is not the same as saying it HCD. Okay? All right, so actually from a terminology standpoint, that's a distinction between the manufacturers. Okay, so if you have a QTOF instrument that comes, say, from SciEx or from Agilent or Bruker, they might call that fragmentation technique CID. Okay, that fragmentation is exactly the same thing as what Thermo calls HCD. Okay, and the reason is that before Thermo created the current instruments, they had ion trap fragmentation that was resonance excitation, and they called that CID. Okay, all right. So they had to have another name for when they did it the same way as other people. Okay. All right. Next. Okay. These are the amino acids. If you knew these by heart, it would be easier for you to look at the mass differences. If you had the opportunity to print them, that would be helpful. So these are some things that's particularly helpful for you to know that we will make use of in interpreting the spectrum. Okay, so an A ion is 28 Daltons less than a B ion, and if you can't decide whether an ion is an A or a B or a Y, and if it has something that's 28 Daltons less, then you can probably call it a B. That's why it's useful. Okay, all right. If you know your amino acid masses, and you just add them all up and add 1, that will give you the mass of the B ion. If you add up all your amino acids and add 19, that'll give you the mass of the Y ion. Okay, and then if you fragment between 2 amino acids, B ion is going to go one way, Y ion is going to the other. If you add them back together, you would have the whole peptide, right? Okay, but when you fragment, so I'm always going to talk about the parent mass as being singly charged, okay? The B ion is singly charged, the Y ion is singly charged, so if you add the 2 together, you get the MH plus 1, okay? And those are complementary ions as shown up here. So B ion plus Y ion is the same thing as MH plus 1, okay? Some software packages, they will strip out the charge. I think that's silly, okay? Because we measure ions, we don't measure masses, right? And furthermore, if you, when when you're dealing with high accuracy masses, you have to trust that they have built to subtract the right amount, because it's not 1.0. It's 1.0078 minus the mass of an electron, okay? And these things matter. So I think it's easier just to think in terms of ions, okay? All right, so I keep the charge. All right, those are the useful things to know. What kind of spectrum would you call this? This would be on the quiz. Come on, what? If you were to give it a cute little name, what kind of? You want to call it a white picket fence. I was going to call it a Royal Enfield, okay? Right? So this is a relatively beautiful spectrum. It's going to have, you can see it's got ions that span the mass range. They look nicely spaced. Okay. All right. So before you start doing some math, okay, so the MH plus is 1,000, okay? This right here is at 500, okay? So if you look, you will see some nice symmetry. Lysine has a Y1 ion that is 147, okay? Arginine has a Y1 ion that is 175. You should now be able to tell me what the C-terminal amino acid of this peptide is, if you're looking at the spectrum. All right? So if this is where the precursor mass is, and you can see that there's some symmetry, right? So these two peaks are about equidistant from the center, and so that means they're probably a BY pair. Okay? So I'm just going to do this kind of thing here. Then I bet you if you look where the red caret is. Okay. All right. And so the other thing you can do to check, if you can't really tell the symmetry, you're going to add up the masses. 414 plus 587 should be equal to 1,001. All right. So similarly, we can go like this. Okay. Those are going to be symmetric. I already told you that if it's a tryptic peptide, Y1 is 175, which would be consistent with there being an arginine at the C-terminus, right? Okay, and that Y1 would be symmetric with 826. That means this should be a B ion. Okay? And then there's probably a couple others in here. So 230 going all the way to 771. Okay? So you can see there's lots of symmetry present. All right, now let's do some arithmetic. My advice whenever you're going to start doing arithmetic is, and you have to choose where to start, make one of two choices. Start with the big peaks or start at an end. Okay? Okay. I'm going to go with big peaks, but when you start at an end, it's helpful it's nice to have one that you already have an ion type for. Okay. One of the things I try to resist doing is starting at the low end. Okay? Because there's more often going to be multiple things happening below the precursor mass. You're going to have multiply charged things. There's going to be internal ion fragmentation. You usually have a cleaner spectrum up at high mass. All right? So now let's just do some arithmetic. Okay, so this mass gap here is 101. No, 58, 13, 71. Okay? This mass gap here is 113. Okay? Then 587 to 513 is 74. That's not an amino acid mass. 488 to 587 is 99. That's an amino acid mass. Okay? 488 to 414 is 74. That's not an amino acid mass. Okay? let's go 826 to 727, that's 99. Okay, 727 to 612 is 115. Okay, 612 to 513 is 99. Okay, 513 to 414 is 99. Okay, all right, can we go 414 to 353? That's 71, right? 343 down to 230, it's 113. So now then I would go 175 to 274 is 99. Okay, 115. All right, then can I go up here? 99. Okay, if this is a Y ion, this should be a Y ion. This should be a Y ion. Y ion. Y ion. Y ion. Y ion. If this is a B, that should be B. 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 B, B. Okay, valine. Oh, let's do one other thing. This is mass 100, 1000, sorry. Can you read that? That's not a fake peak. We know that is reasonable because we measured the precursor mass before we did the MSMS spectrum. The precursor mass is 1000, okay? All right, so, and then if it's 1000, we can go from here with 129. Precursor mass is like a Y ion. It's like the last Y ion. Okay, so now we could write down the sequence. And if we go with Y ions, we would write down the sequence backwards. Okay, arginine already, 99 is valine. Isoleucine is 113. No, wait a minute. Okay, what leucine is 113, but yes. So when you do de novo sequencing, usually if we can't tell, we just choose leucine. And I think the simplest reason is that there's 6 codons for leucine and 3 codons for isoleucine. So if you can't tell, might as well go with the chance it's got more codons. All right, but at the end of the day, no, I can't tell that it's leucine rather than isoleucine. Okay, 115 is aspartic acid. Okay, 99 is valine. Okay, where are we here? 71 is alanine. Okay. 90, so there's a bunch of valines here, right? Alanine. 115 is aspartic acid. That's valine, and this is glutamic acid. 129 is E. Okay. All right. There's a whole lot of junk on the spectrum on the page now, but if I follow it carefully, this 99 would be valine, and it would be aspartic acid. And it would be another valine, and then another valine, and alanine, leucine, and glutamic acid. Okay, and now if we try to read off the B ions, let's see if we get the same thing. So we got leucine. Nope. We have leucine, alanine, valine, another valine, aspartic acid D, and then valine, and then we would go all the way to here in the arginine. So it looks like there's something that's not quite right. Okay. So what did we do wrong? So I said ELAV, and then, oh, is it going to be? I got it partly backwards, huh? No, VD, VD, ALE. Okay, so the E is not right. Should be ND. And why is that? All right. The E, how did I have the, oh, that's, so I can't do, I have bad math, okay? So this is 229. All right, it's not 129. Okay, so we need, and that's, right, that matches this B1 ion here, okay? So we have some combination of amino acids that adds up to 229, okay? Okay, and there's a couple of ways you can do that. You can do 115 plus 114. And that is D and N. Okay, so if we now take a look at the way that this spectrum is labeled, we don't have fragmentation between N and D. So this would start at 230, and then this last gap here is 129. Okay, so the sequence is complete with exception we don't know the order of N and D. Okay, so from a pure de novo standpoint, we don't know whether it's ND or DN. Okay, but if we then add the requirement that this peptide has to come from the human proteome, turns out only one of those two choices is present. Okay, right, and so it's the ND part. All right. So let's go to the next one. Okay. So this one is going to be easy because there's not very much to work with. All right. So you take a look at the spectrum. There is not a lot of symmetry. But there is, if you look at this, this is doubly charged. Okay, 2 times 480 would give you 960. Right? There's 2 charges on this. There's only 1 charge on this. All right. What else have we got? Okay, this is 1220. Is there any symmetry here? 262 to 959. That should be a BY pair, I think, right? 221, okay. And then the mass difference between these two is 28. All right. What's the ion type of the peak at 262? Okay, this was one of the things that I gave you of useful information. The difference between a B ion and an A ion is 28. So we could assign that as A and that as a B ion. If this one's a B, then that has to be Y. Okay, what else can we do here? So then that would mean that this is Y doubly charged. Okay. Then if we take a look at this mass gap, that's 97. And that mass difference, 25, is 87. Okay, that's serine, proline. All right. All right, there's not a whole lot else here. So we don't have down to low mass. Okay, but so at some point there's some sequence here. That is PS, and then the distance here is something that adds up to 261. And then the distance out to here would be 775. This one comes from a tryptic peptide experiment, and so there should be either an arginine or a lysine here. Okay, that's about all the information there is in that spectrum. Okay, there's the PS part. That's about all the information there was. That information all together is enough to produce that one answer as a peptide from the human proteome.
In today's hands-on session, you were introduced to the fine points of mass spectrometry based data interpretation. The spectra, they are having all the information, but how to get the most relevant information. Think about if you are locating even the post-translational modification such as phosphorylation or even glycosylation, the data interpretation becomes very crucial and very challenging. However, in today's hands-on session, Dr. Clauser tried to explain you how to get the best interpretation from these complex spectra and even to glide into the PTM based analysis. As it was discussed in today's lecture, the B ions differ from the A ions by a mass of 28 Daltons. This observation helps in better understanding and differentiating various fragments. In the next session, you will be provided with comprehensive information on interpretation of further more complex spectra. Thank you.